and welcome to Swecodes. Today, we're diving into one of the most fascinating tournament simulation problems, Leetcode problem number 1900, the earliest and latest rounds where players compete. This problem beautifully combines dynamic programming with bit manipulation, and I promise you, by the end of this video, you'll not only understand this problem inside out, but you'll also gain valuable insights into solving similar tournament-based challenges. Let's begin this exciting journey together. Alright, let's break down what this problem is asking us to do. We have a tournament with n players, numbered from 1 to n. Here's the brilliant part: in each round, the first player competes against the last player, the second player against the second to last, and so on. When we have an odd number of players, the middle player gets a free pass to the next round. Now, here's where it gets interesting. We have two special players who are unbeatable against anyone except each other. Our mission: find both the earliest and latest possible rounds where these two champions could face each other. We control the outcomes of all other matches, which gives us the power to manipulate when our special players meet. This is a classic optimization problem disguised as a tournament simulation. Let me show you exactly how these tournament rounds work. Look at this visualization with 11 players. See how player 1 pairs with player 11, player 2 with player 10, and so on. Notice that player 6, being in the middle, automatically advances to the next round, no competition needed. This pairing mechanism is crucial to understand. After each round, the winners are rearranged in their original numerical order. This isn't a random bracket. It's a structured system that maintains the relative positions of players. This ordering constraint is what makes our problem both challenging and elegant. Let's walk through a concrete example with n equals 11, first player equals 2, and second player equals 4. In round 1, we start with all 11 players. Since players 2 and 4 are our special players, they must win their matches. Player 2 beats player 10, and player 4 beats player 8. Moving to round 2, we now have 6 players remaining: 2, 3, 4, 5, 6, and 11. The survivors are always reordered numerically. See how players 2 and 4 are getting closer to facing each other. And in round 3, with only players 2, 3, and 4 remaining, our champions finally meet. Player 2 faces player 4 directly. This happens in round 3, which could be either the earliest or latest depending on how we manipulated the other matches. Fascinating, isn't it? Let's understand what we're really solving here. We're looking for two values: the earliest round and the latest round where our special players can meet. We have complete control over non-special match outcomes, which means we're essentially finding the minimum and maximum paths through a tournament tree. The key insights are: first, both special players always win until they meet each other. Second, we can manipulate other matches to either bring them together quickly or delay their meeting. Third, winners always maintain their original numerical ordering. This is a dynamic programming problem at its core, enhanced with bit manipulation for efficient state representation. We're dealing with tournament simulation, which puts this in a special category of DP problems. Understanding these problem characteristics will guide our solution approach. Before we dive into the solutions, let me give you some powerful hints that will illuminate the path forward. Hint 1: think recursively. Each round reduces our problem size. The key question is, can we efficiently track which players remain after each round? This recursive structure is the foundation of our solution. Hint 2: use bit masks. Instead of maintaining arrays of remaining players, we can represent them as bits in an integer. Player I is in the game if bit I is set. This representation makes state tracking incredibly efficient and enables memoization. Hint 3: memoization is crucial. Many game states will repeat as we explore different tournament paths. By caching results for each unique state, we transform an exponential problem into a manageable one. Without memoization, this problem would result in time limit exceeded. Let's start with the brute force simulation approach. This is where everyone should begin, understanding the problem through direct simulation. We'll simulate all possible tournament outcomes by trying every possible winner for each match. When we encounter a match involving our special players, they must win. For other matches, we explore both possibilities. We track when the special players meet and update our minimum and maximum round numbers accordingly. The implementation involves recursive exploration of all tournament paths. While this approach has exponential time complexity, 2 to the power of n times n, it helps us understand the problem structure. The space complexity is O(n) for the recursion stack. This approach works for small inputs but will time out for larger values of n. Here's our Java implementation of the brute force approach. Notice how we start by creating a list of all players. The simulate method is our recursive workhorse. It checks if the special players meet in the current round, and if not, it generates all possible outcomes for the round. The key logic is in the pairing mechanism. We iterate through the first half of the players, pairing each with their corresponding player from the end. When we find our special players facing each other, we update our result array with the minimum and maximum round numbers. The generate outcomes method explores all possible match results. For each match, if it involves a special player, that player must win. Otherwise, we try both outcomes. This branching creates our exponential search space. See how clean and understandable this code is. That's the beauty of starting with brute force. Now let's see the Python implementation. Python's elegance really shines here. We use list slicing and comprehensions to make our code more concise while maintaining readability. The simulate function follows the same logic as our Java version. We check for meetings between special players, then recursively explore all possible tournament outcomes. Python's dynamic typing and built-in functions like min and max make our code particularly expressive. Notice the use of float, inf, for initialization, a Pythonic way to represent infinity. The recursive structure is identical to Java, but Python syntax makes the algorithms flow even clearer. This implementation, while still exponential in complexity, serves as an excellent foundation for understanding the problem. Now, let's level up with dynamic programming and memoization. This approach recognizes that many game states repeat during our exploration. Our state is defined by the bitmask of remaining players and the positions of our special players. By caching results for each unique state, we avoid redundant calculations. The recursive structure remains the same, but now we check our memo table before computing. The implementation uses a hash map to store results for each state. While the worst-case time complexity remains 2 to the power of n times n, the practical performance is much better due to memoization. The space complexity increases to 2 to the power of n to store our cached results. This approach can handle all test cases within time limits. Look at this beautiful Java implementation with memoization. We create a unique key for each state by combining the bitmask and player positions. Before solving any state, we check if we've already computed it. The solve method extracts active players from the bitmask, checks for special player meetings, and recursively explores possible outcomes. The key optimization is storing and retrieving results from our memo map. This prevents us from recalculating the same tournament state multiple times. Notice how we ensure consistency by always keeping first player less than second player. This reduces our state space by eliminating symmetric states. The memoization pattern here is a textbook example of dynamic programming optimization. The Python implementation showcases the language's strength in handling dynamic programming. We use a dictionary for memoization, with tuples as keys for immutable state representation. The solve method elegantly extracts active players using bit manipulation and list comprehension. Python's tuple packing makes creating state keys natural and efficient. The recursive exploration remains the same, but now we're leveraging Python's built-in hash table implementation. See how we use the walrus operator or traditional assignment to handle memoization. This pattern of checking the cache, computing if necessary, and storing the result is the heart of dynamic programming. The code is both efficient and highly readable. Time for our most optimized solution, Optimized DP with advanced bit manipulation. This approach squeezes out every bit of performance while maintaining the same algorithmic complexity. We optimize by pruning impossible states early and using more efficient state representation. Instead of string keys, we pack our state into a single long integer. We also implement smarter backtracking that avoids exploring obviously suboptimal paths. The key optimizations include early termination when we detect impossible scenarios, bit manipulation tricks for faster state transitions, and minimized state space through symmetry elimination. While the complexity remains O(2 to the power of n times n) time and O(2 to the power of n) space, the constant factors are significantly improved. This Java implementation represents the pinnacle of optimization for this problem. We use a single long integer to encode our entire state. The mask, first player position, and second player position are all packed together using bit shifts. The DFS method showcases advanced bit manipulation. We extract active players efficiently and check for special player meetings. The state encoding uses bit shifting. Mask 10 leaves room for player positions, each taking 5 bits. This allows states up to 2 to the power of 10 players with positions up to 31. The try-all-outcomes method implements intelligent pruning. We avoid exploring branches that can't lead to better solutions. This optimization, combined with efficient state representation, makes this implementation lightning fast. This is production-ready code that demonstrates mastery of both the algorithm and the language. Our final Python implementation leverages the functools.ru_cache decorator for automatic memoization, Python at its finest. This approach is both elegant and highly efficient. The nested backtrack function implements our match outcome exploration. For each match, we determine if a special player is involved and handle accordingly. The use of non-local variables for earliest and latest allows clean state updates within our nested function. Notice the beautiful symmetry in how we handle different cases. Special players must win, while for regular matches, we explore both outcomes. The bit manipulation for next_mask construction is crystal clear. This implementation combines Python's high-level features with low-level bit manipulation for an optimal solution. Let's analyze the complexity of our three approaches. All three have the same worst-case time complexity of O(2 to the power of n times n, but their practical performance varies significantly. The brute force approach explores every possible tournament path without optimization. With O(n) space complexity, it's memory efficient but time prohibitive for larger inputs. It serves as our baseline for understanding the problem. Dynamic programming with memoization maintains the same time complexity but dramatically improves practical performance. The O(2 to the power of n) space complexity is a worthwhile trade-off for the speed gain. Most states are visited only once, making this approach feasible for all test cases. Our optimized DP solution keeps the same complexity but with better constants. Congratulations! You've just mastered a complex tournament simulation problem that combines dynamic programming, bit manipulation, and recursive thinking. Let's recap our key takeaways. First, we learned how tournament simulations can be modeled as state space exploration problems. Second, Bitmask DP provides an efficient way to represent and track game states. Third, memoization is absolutely crucial for avoiding time limit exceeded in exponential problems. Understanding when and how players can meet in a tournament structure is the core insight. This problem pattern appears in various forms, from tournament trees to winner prediction problems. Practice similar problems to reinforce these concepts. Remember, every expert was once a beginner. You've taken a significant step in your algorithmic journey today. Keep practicing, stay curious, and happy coding. You've got this.